So it's a pleasure for me to introduce Dr. Ayan Mitra, who is our speaker today. So Ayan did his master's at Sussex, and then he did his PhD in France, and then he was a postdoc with Eric Linder in Kazakhstan, and now he's a postdoc at the Inter-University Institute of Astronomy and Astrophysics in Pune in India. So today he's going to talk about supernovae, and should also mention that he's applying for a CAPS fellowship for this year, so there's a chance that we might see him again.
Thank you for the introduction. So thank you everyone for coming, and I'll also join in the pizza afterwards. So let's get started. I hope with due course more people will come. So anyway, I've been introduced, but I'll go through it once more. So I'm Ayan. So I'm at the moment working in the LSST desk, and so I'm an in-kind contributor in that respect from India, Ayuka. And so today I'm basically going to give a talk about doing supernova cosmology with photometric samples and using photometric redshift specifically. So like the name suggests, it's using a plastic supernova 1A cosmology using host photo Z. And this work I have been doing in association with Richard Kessler, who is from Chicago, and also the wider LSST desk group that includes people like Gautam and Co, etc. So we recently just the result that I'm going to talk today is just recently been online, so the paper is accepted. Anyone of you interested can go on archive and check it. And so I'll get started. So roughly this is going to be what's the outline of today's talk. So we'll go through an introduction, a bit of recap, what was the background flavor, and then we'll talk about the data that's been used for this analysis, that is for the SNIa simulations using the plastic supernova 1A data. Then we'll go on and talk a bit about the cosmology, the actual analysis of and what sort of redshifts have been used from supernova and host photometric redshifts, the different type of systematics that's been considered, and their implications. And finally, we'll give a comparative study of the results, cosmological results of using spectroscopic sample only, and in contrast using a spec plus photometric redshift for dark energy constraints. And then we'll end it up and we'll talk a bit about the future and what holds in the immediate LSST pipeline with respect to this work. So I'll take a couple of steps back. So those of you who are not familiar with SN cosmology, or even if you are, this is a very coarse overview of the map of SN cosmology, let's say in the last 20 years. So for the best part of the last 20 years, when we talk about SN1A cosmology, we're talking about basically this first row, spectroscopically classified samples with spectroscopic redshift, and typically would be called as the gold sample. For example, the Nobel Prize that was won was used such a similar data set. Moving down the line, the next stage of evolution of SN cosmology was where you would have the provision to use photometric classified samples, but you'd still use spectroscopic redshift. Few results from PS1 Dark Energy Survey from David Jones were exhibiting such kind of analysis. And then, as we move ahead, the next stage would be, or as is understood, was using a spectroscopically classified still, but with the provision of the possibility of using photometric redshift that could be host, as of now, host only. So spec plus host, a combined sample for the redshift. And there was a few low stat demo papers on this, but not really on the large scales. And this is why exactly this analysis that we have done comes into the picture. So our analysis, which you call as M22, so stands by my name Mitra 2022, we did this on a proper, rigorous, extensive analysis where we used a photometric redshift and did a full cosmology with supernova 1A within the frameworks of LSST. We'll come back to these slides a bit again in a bit towards the end of the talk, and we'll see where it's with respect to it is in the future holds. I'll take another step back to do a bit more recap as to in order to explain the wider picture as why is this important and what culminated towards this research. We have been publishing papers in this series similar to this, where we have been working on photometric systematics, for basically supernova redshift systematics, mostly in focus with LSST and then first we published a paper which is, as the name suggests over there, so photometric supernova redshift systematic requirements, and then we followed it up with an additional paper where we not only had LSST in focus, we also included a Roman and tried to further explore what is the cosmology requirements of if one were to use a photometric redshift for supernova 1a. And the broad conclusion that we got, I'll not delve much into the mathematics of it, but the broad conclusion that was out of both those papers were very similar, which was basically saying that low Z photometric or photo Z bias and outliers were the most dangerous, irrespective of, even if you use Roman, for example, combination with near infrared data from Roman still showed that spectroscopy is still necessary for low Z. And so this is the probably the money paragraph of the whole paper, so I'll read it out. So, however, overall the main redshift estimation improvement is at high redshifts where cosmology bias is less. The sensitive low redshift show relatively little gain, so even in the era of LSST, Euclid and Roman, low redshift spectroscopy of supernova host galaxies will be quite important for enabling the full potential of dark energy constraints from SN cosmology through time domain surveys. With that in the background and those, we set out to do this analysis, so which is the current analysis, where we were focusing on only LSST-based data using plastic simulations and further explore what was the possibility of doing cosmology photometric candidates. So, like I mentioned, plastic multiple times, so most of you probably who are familiar, but those who are not, plastic stands for Photometric LSST Astronomical Times Risk Classification Challenge. This is the data from which we derived our full simulations on. So in our simulations, we use the DDF data. DDF stands for Deep Drilling Field, which is one of the two observing strategies that the LSST have, the DDF and the WFD, White Fuzz Deep. We only used the DDF data. We used supernova 1A only candidates. That is, there's no contamination of different types of supernova or misassociated hosts, etc., etc. Because we only wanted to focus on the systematic effect from pure supernova 1A sample. And then for the small subsets where spectroscopic redshift were available, we used those redshift from the foremost forecast. And host photometric redshift was based on the paper from Melissa Graham, so Graham 2018. So all this together, we had to put it in a pipeline and get it cooked to get the final end product. For that, we used what is called the publicly available software called SNIa, stands for Supernova Analysis. It's been used simulation to generate realistic supernova 1A light curves for LSST observations, and the codes were also used for doing light curve analysis. For binding this whole process end to end, we use what is called as the PPIN for this workflow. So here is a single slide rough overview summary of the simulation stages. So basically, like I mentioned, so that we use the plastic supernova 1A, and then we also supplemented it with some low redshift additional samples, candidates of SN1A. This was derived from the WFD, as I mentioned before, the White Fuzz Deep in DC2 data. And we had, in addition to that, a high stat unbiased core sample, which is done for the bias corrections in the results. For those of the cases, like I mentioned before, that spectroscopic redshift were present, they were determined by the efficiency map of foremost. In the case where spec was not available, zspec, redshift was determined from the photometric redshift and the corresponding photo Z error. One of the main stages during this whole simulation and the analysis pipeline in SNIa was the light curve fitting stage. So the most interesting part that we had or the most novel part we had was the application of the 5-parameter photo-z fit, which was used with the host redshift. It could be spectroscopic or photometric as a Gaussian prior. And then once we pass those stages, we end up in this stage was a bias corrected Hubble diagram is produced. Then we produce a covariance matrix, which is a combination of stat plus syst. And then finally we come to the stage of cosmology fit, where we used SN1A plus CMB prior. This was done with fast cosmology fitter program called WFIT. Right. Here's a single more, for those of you who like to see more colorful plots. There's a graphical representation of the analysis pipeline. So you have a stage 1 standardization of the supernova brightness with light curve fit. Then you do the simulations for the bias corrections, and then you produce the Hubble diagram, and finally you have the cosmology fitting, like mentioned before, with the WFIT program. So we have here in this slide, we see a couple of examples of the light curves that was being generated. For example, on the left you see one from the low redshift WFD, one candidate at Z is equal to 0.05, and we see one on the right similar but at high redshift derived from the DDF field, so at Z 0.91. Each of those are shown in a mosaic of 6 plots corresponding to the 6 LSST passband filters U, G, R, I, Z, and Y. Yeah, this is an example. And now we come to the quality of the photometric redshifts that's being used, and so we look in the photo-z residuals that were considered. On the left that we see is a plot of the full host catalog. So like the name suggests, this is the full house. Every candidate is plotted there, and the residual basically is a function of the Z true. On the right that we see is, like it says over there, it's after the trigger and selection cuts. So you throw away a lot of candidates based on your quality checks with solved to fitted redshift that is used for Hubble diagrams. So the plot on the right that you see is basically the science case, and those are the candidates that goes in for the Hubble diagram generation. And as the red bold point suggests, that the solved to fitted Z4 has 40% better resolution compared to the one on the left, and 20% fewer outliers. And this goes in for the science simulation subsequently. Cosmology results. So the final sample, like I mentioned before, contains a mix of spectroscopy candidates and photometric candidates. So it's combined together. So you have the spectroscopy candidates at low Z, which shows, if you see the red bars in the bar plot, and then you have the photometric candidates colored in blue, more populated towards the right. For the moment you can ignore the green bars, but I'll give a one-line definition. So basically they're called z-gt, meaning that they corresponds to the true redshift. We used it as a benchmark, just as a benchmark, to see what could have been the maximum improvement obtained, but it's apart from that there was not much further consequence to it. So the redshift beamed Hubble diagram is produced from those. So you already saw the beans over there, which is then used for cosmology fit. And I did mention in one of the earlier slides that we considered different kind of systematics. So here's the list of systematics that's been considered for the covariance matrix. Broadly, they could be classified into 2 categories: the calibration systematics and the redshift systematics. So like calibration HST, 0 point, LSST filter shifts, the redshift corresponds to spectroscopy, photometry, etc., etc. And then on the top we have the stat only case, which we considered, and on the bottom of the table that you see we consider the all systematics, which is stat plus syst all combined. So now this is another example of a typical Hubble diagrams that's being produced during the simulations. So on the left, as usual, the color codes of red, which corresponds to the spectroscopic sample, and on the right is a photometric sample in blue. And so we see the lower panels of each of those plots corresponds to the Hubble residual. Like it's evident that there's no apparent systematic trends in the residual plots, and also you could notice the extra range on the x-axis, that the z-foot goes beyond the red bar. So yeah. Having produced the Hubble diagrams and moving towards the cosmological analysis, one of the most important aspect was understanding the distance estimates and how much were the uncertainty budget involved with it, right? So here's a plot that you see as a comparison between the spectroscopic redshifts distance uncertainty, the sigma mu, and the photometric in blue. What we see most importantly is that for low z, that is z less than 0.6, the distance precision is similar. They're very much in agreement between both of them, the spec or the spec plus photo z candidates. However, as you go towards the right, z greater than 0.6, the spec plus photo z case, that is a blue case, have significantly smaller uncertainties on your distance estimates. And as you go more right, so at high z, your spec plus photo z behaves much better. This can be further contrasted if we overplot with what I said before, the z-gt. Again, it's just for a comparison, not for a science case, but there's minimal improvement. So what I'm basically trying to show here is that your photometric sample is almost to the maximum accuracy that you can achieve if you contrast it with the Z-true cosmology. It's within a few percentage of difference. And so this brings me to one of now the cosmology results.
Ryan, can I ask you a question on the previous slide?
Yes, please.
The millisegram photo Z code spits out redshift uncertainties, but those uncertainties you're treating as just purely Gaussian.
Yes.
Yeah. So why isn't this just telling us that the central limit theorem works, that as you get a higher and higher redshift in a photometric sample, you have more and more Gaussian PDFs that you're averaging together, and sure enough the uncertainty goes down? Real photo Z PDFs won't be Gaussian at all.
I missed some part of it. If you come close
so
to
real
the
photo
mic.
Z probability density functions won't be Gaussian.
Right.
Whereas the model you're using from Graham et al. Is just a bunch of Gaussians. And so you're averaging ultimately, considering that sigma mu ultimately goes to sigma z, just a bunch of Gaussians on the right-hand side. And of course, all that's saying is the central limit theorem works. So this doesn't shock me. And will it hold if you have more realistic photo Z uncertainties?
Right. So the question, the answer to the if it hold to more realistic photo Z, as of now, the latest information that I have is, I haven't done it myself, but someone called Rebecca Chen is doing exactly similar at Duke's. We had a chat on that. Preliminary results show that there is not much improvement compared to this. It's very similar in there. So, but a concrete number I can't give you, but in due course we'll see that. Yeah, thank you. Yes.
So what sets sigma of mu?
Right, so mu is your distance modulus. So if you have the supernova distance formula, which is mu is equal to your x function of c, which is like stretch, color, and big M, and then something. So that is how you compute your distance modulus. And then this sigma of mu is saying how much is the uncertainty on the distance estimates, right? As a function, if you were to use basically with a spectroscopic sample if you compute, or if you spectroscopy a photometric sample you compute.
But why is that different for the two samples? Is it just...
So the difference is because of the n, number of samples. Oh. So as you go on the higher, so if you go back to this bar plot.
These are binned.
Right, so this bar plot gives you, right? So as you go high, so it's 1 by root n, it's...
Okay, I got it, thank you.
Right.
Okay, thank you.
So this brings me to basically the cosmology plot now, which is the most important. So what you see here is a two-dimension dark energy plane constant plot of W0 WA, that is the equation of state parameters. This is only shown in red, meaning there are only the spectroscopic samples, and there's two lines. One is solid, one is dashed. So basically, one is a stat plus syst, and one is stat only, as shown in the legend. And you have the figure of merits given there, which is computed based on the dark energy task force report as basically sigma of W0 and WA. So this is some numbers. Have a look. Now, if we were to compare this with the photometric samples, so each of those solid to solid, dash to dash, if we compare in both the cases, these photometric samples have for figure of merit much tighter compared to its red counterpart. So much so that the improvement is almost 50% in your figure of merit for the photometric samples in comparison to your spectroscopic sample. Yes. And we also looked further into the question of which are the systematics which is basically eating away your figure of merit, or degrading your figure of merits value. So what we show in this table is basically a ratio of FOM syst I, meaning corresponding to the individual rows, divided by FOM stat, that is the top row, which is the maximum FOM, right? So if you see your FOM at the top is 1 because it's the same, and then as you go down the table, your FOM ratio goes down, meaning there's the degradation in the, so it's sorted basically as we show in the table. So the bottom part of the table shows you that the calibration systematics ratio of FOM is 0.63, which basically tells you that FOM degradation is dominated by mostly calibration systematics. So remember, in the final cosmology, you will take a stat plus syst, so you will have all those systematics going in, but essentially those calibrations are the ones, the biggest culprit, which will eat away your figure of merit values. I would also like to mention that apart from those single data realization cosmology, we also simulated 25 individual statistically independent realizations and did the entire same full sample analysis that was done for the one simulation for 25 individual cases. And we did that to basically estimate the bias. So we did 25 simulations, and then we computed the weighted mean of those. And so what you see over here overplotted on those ellipses are those crosses, which basically shows what your biases are. And as is seen, they're very much consistent with 0 values. So there is no apparent bias we can infer. Going on that same note, I would like to mention that there's a big community discussion going on about using binned or unbinned Hubble diagrams for cosmology computation. And we know that unbinned results have produced smaller uncertainties, like from paper from Dylan Brout. We also tried that, but unfortunately the unbinned result produced large bias in our case. And again, it was caused by the calibration systematics. So while they were producing smaller systematics, tighter constraints, which we understand, but we couldn't get the bias to go away. And so we're still working on that. So there are several investigations have been on the way, which includes one of them is a numerical precision of inverting a big square matrix, or with or without a speed trick, like the speed trick, because it takes a lot of time if you have a big covariance matrix. But in future work, we hope it will be fixed and we will be able to produce an unbinned Hubble diagrams cosmology results. So here's just to give you a flavor. So if we did an unbinned analysis, those crosses that we saw in the previous plot now goes that much far. So that is what I mean by the bias gets really off, and so we can't use that for cosmology. There's a ratio of the figure of merit, and which shows how much improvement you could get unbinned by binned if you were to do cosmology with them. But because of that, we had to leave it out. And so this brings me to my conclusion, which basically says adding supernova plus host photo Z significantly improves average distance measurements for high Z, that is greater than 0.6. the FOM, the figure of merit, W0, W for equation of state parameters, improves by almost about 50%. And this includes the systematics, which is in contrast to, let's say, some previous results, mostly where people would only consider statistical. Hubble diagram now extends 0.3 units further in redshifts, like I mentioned before, so you have a bigger Hubble diagram. And analyzing 25 simulated data samples, the average bias on W0 and WA is consistent with 0, like we saw before. I would also like to mention that we did try with WCDM as well, apart from W0 WA cosmology. There's minimal improvement, that there is improvement, but it is not as stark as what we saw here using Photo Z. And while this is the conclusion, I would like to just mention a bit what's in the pipeline and what's coming. So now we go back to one of those initial slides, and now we have an additional row on the bottom. So we were here already, we did a spectroscopic classification and a photometric redshift. Now we have started working on the next project. It's a big project, so we will have photometric classification and a full sample, which includes spectroscopy plus photometric redshift. This is quite a gigantic work, I would say, and that started just a few days back. So we have this rolling. So what that will mean is that now, in addition to the previous analysis, we will have core collapse contamination in simulations. We will use misassociated hosts in the simulations, and that brings into the picture of the photometric classifiers and beams to be used for the analysis. And that's end. Thank you.
I will say you should probably explain what beams is for the non-supernova people in the audience.
The people here sitting are more knowledge about beams than me talking. But so, I mean, do you really want me to go through that?
No, so let me ask you a question, I guess. So you did this, you checked the average of 25 different simulations, but ultimately all of them had WA consistent with 0, right?
Yes.
Did you ever put in a non-zero WA and see how many supernova it took in the...
No, we didn't.
So that would be an interesting question to answer.
We didn't do that. Neither did it. It crossed my mind I should talk about that with Rick, but...
I mean, you can leave W0 at -1 and make WA just ever so slightly non-zero. Obviously, that's desk's entire arrays on the array. So...
Yeah. No, I can do that very quickly because the simulation is all that. It's just one step, last stage. So I'll take this input from you and I'll go back and try to see that. Thank you.
Ayan. Yeah, sorry, you said the bias is 0, but I thought the first plot that you showed...
I mean, I'm not saying with 0. I'm saying it's consistent. I mean, it's if you zoom out, that's a very tight constraint. And
so for zspec, that's like more than 1 sigma, right?
Yeah, but if we were to compare with this, there's a bias, but it's minuscule still.
Sure, but it looked like you also tweaked the bin size just to make sure that the bias is vanished. How did you pick the bin size here?
So here is so bin size. So I don't know if I explained wrong. So bin is fixed. So there's 12 bins.
Sorry.
Right.
So later you said unbinned results are more biased compared to the binned results.
Right.
So how did you pick the bins?
So I'll just go through this once more. So what I mean is unbinned and binned. So basically, so you have the binned one. So you have, let's say, 12 bins like that. You do the full cosmology with bins, and you do the W0 W estimation and the corresponding sigma, etc. And then you do that 25 times. All of them, just mean it by 1 by root over standard deviation. Unbinned is you have no bins. So 5,000 supernova candidates, whatever, 5,000 candidates. You compute for each of them your W's, everything, and then you just do the full mean 1 by root over n. And so now, may I ask you one thing? So where exactly the binned question is?
I'm just wondering why did so are you just saying in the unbinned results your results were just skewed by some wrong supernovae, or is that
No, we are. So, what is causing the bias in unbinned? It's still a ghost to us. We're figuring that out. If we knew, we would have fixed it. But however, some question like we know people in DES, dark energy survey, reported to us that by some mysterious way it's vanished. No one knows how, but we are working on that. But that is one aspect. But if you're asking why it's improving using unbinned, the constraints, I would suggest you to please go and read Dillon's paper. It has a full paper, like exactly like how using full cosmology sample without binned can improve your.
Yeah, that I totally understand.
Okay.
Okay, I'm just. Yeah, I think it's fine.
Yes, please.
Also related to that, weighted mean. So if you just have those plots that show the bias and it just says weighted mean.
Yeah.
Well, first of all, so for binned versus unbinned, so for each simulation, you just like sum up the you multiply all the likelihoods for each of the.
Yeah. So you have one full realization, 2, 3, 4, so everyone identical to each other, same pipeline. You get the results, 25 of them. You divide by root over standard deviation. That's your. You find a W of all of them, so sum, mean, and then you just weighted mean.
W for each supernova, or you
each beam.
Combine them all to get a single best fit W for all.
Single best fit for one simulation. Single, right? So you have 25,
Yeah.
and then you weighted mean, which is the standard deviation, which is root over at 25.
So why don't they all have the exact same weight?
Exact same weight.
So the simulations, wouldn't they all have the same weight?
No, okay, right, no. So each simulation will have some of its individualistic difference, minor, if that makes sense. Yeah, so there's the light curve fit stage, and there's light curve selection stage has some of its intricacies which produces some differences. But statistically they wash out. Yeah, that's right.
This just seems very strange.
Yeah, I mean, if it's just Gaussian error, I'm confused why the binned results will look. I mean, I understand that the error bar will increase because you're kind of like diluting your thing, but I'm slightly confused about systematic.
Yeah, I mean it's still a work in progress. I mean, on this we're looking into it.
Just to follow up that, so you presented so many systematic things, right? So it looks like you probably have a very good model for systematic. So have you actually tried to marginalize over some of these things and see if the bias goes away?
Can you repeat the last part, please?
So you seem to have a pretty good knowledge about systematics here. So
right.
I'm just wondering if you tried to marginalize over some of, I mean, if you can come up with a model for this and marginalize over this.
We haven't done
of the bias in, and see what you get.
We haven't done that.
You have that?
If you're asking if we did the marginalization.
Over the systematic errors.
No.
Okay.
Right. Yeah.
I have a question, Ayan.
Please.
So your slide about future work, about like core collapse contamination and associated hosts. So you said you're doing all this work within PLaSTiC, but is there any work that you're going to do with the follow-up elastic sample, particularly because those have associated hosts with them and all these things? Are you planning on doing any of this with the elastic sample?
Good question. So we proposed with PLaSTiC at the moment. It's just the first week. There's a lot of things that we would like to discuss. For example, we used DDF. We don't know how much DDF WFD will go in. The photo Z modeling, the spectroscopic foremost modeling. All these are up for debates in the upcoming sessions in desk, and the classifier and the PLaSTiC and etc. So it's very much in the nascent stage. It might be, but I can't answer for now. It's just
I mean, I'd quickly follow up his question by saying, yes, you should absolutely use Elastic, and mostly because I think the host PhotoZs are done a lot better. In fact, there's a whole paper about that by Locken and Galliano, also in AppJ recently.
I was reviewer to that paper.
Yeah.
So yeah.
There's making things non-Gaussian is hard and worthwhile doing. But on a related note, you've done all of this stuff with simulations. Say you had access to a sample of, roughly 2,000 supernovae, including misclassified type 1a supernovae, and they're all predominantly at low redshift, say from something like the Young Supernova experiment. How quickly could you adapt this machinery that you've developed for the simulations to do a real cosmology with a real analysis?
So realistically, I see this is not the question that I'm facing for STEM. I've been asked already before in desk. So we on a good scale, we think it could be quite quick, basically, because the pipeline is very much ready. I see it in 3 to 6 months. It could, optimistically, within a 6 months frame, it could be definitely be. Yeah. But of course, from past experience, like you all have had, you think one, but in science you end up with some roadblocks. But as of now, because we have traversed the full pipeline, and it's just additional plugins that we need, so we can do it quick. Actually, I believe, yeah. And we also would like to mention that in this future work, so that there's a of course, there's a central paper that is linked with it, but we think 4 to 5 supplementary papers that will be linked to it will come in due course over the period, let's say next 2 years. There will be Host Galaxy Association as a paper. There will be as the real LSST data would come in, let's say in 2 years' time, that will release scopes for another 2 papers. So the future with this project, we see quite a bunch of good papers, 3 to 4, maybe 5.
Yeah, and actually, can you tell me on the same vein what your plans are with Roman? You mentioned you had the one paper for Ruben and Roman joint analysis with Eric. And of course, now NCSA is now thinking of joining one of the Roman project investigation teams. So what would you do if you had the combination of Roman and Ruben data?
I mean, last one, we had been very much concentrated only on LSST desk plastic data because that was the pipeline. But in due course, we would like to, and just very similar to what I did with Eric, we just combined with Roman, but now on a bigger scale, properly, like with simulated data from LSS. And if we have access to similar data and priors from Roman, we could just, that's what. I think we discussed this once with Rick, was a possibility, but if there is access, we would like to do that. So there's, like I mentioned, there's a lot of scopes for different papers in this project, and with people coming in the community, we can do a lot of good science stuff. Yeah. Thank you. Okay.